Hello everyone, welcome to Spark Study. In this video, we will study about the RS criteria. We have a special case. In the last two video, we have studied the RS criteria thoroughly, and we have also solved some problem. And in this video, we will study about a special case which indicate the first element of any column. So, okay, the first element of any row, it should not be column. The first element of any row is 0, but other element is non-zero. Okay, that means first column of any row. Just typing mistake. Okay, like this. So this is the array table. You can see here in the coefficient of a square kind of thing, this becomes 0. Can you see, if any term here becomes 0, our formula is to find this next element. Formula is this into this, fine, minus this into this, divided by this. So when you divide 0, this becomes infinite, and we have not studied about this thing. So how could it be possible? I mean, the coefficient becomes infinite. That is not possible, right? So we have to do some action to overcome this 0. Okay, let us see with the example directly. How do you do that? Let's say we have a equation s to the power 4 plus s cube plus 2s square plus 2s plus 3 equal to 0. This is if this is no missing power, so you can say s to the power 0, s to the power 1, s to the power 2, s to the power 3, s to the power 4, and the coefficients are also same sign. Okay, so there is chance, I mean, the system is there is no chance of instability. The system may not go unstable, but the system can go stable. There is chance of the system can go marginally stable. Okay, let's see, we'll design the array table. You can see what happened. So the Raut array is like this. So we write s to the power 4, s to the power 3, s to the power 2, s to the power 1, and s to the power 0. Okay, so the coefficient, like s to the power 4 coefficient is 1, then 2, then 3. So we write 1, 2, 3, then 1 and 2, 1 and 2. And if you once you do that, 1 into 2 minus 1 into 2, that is 0 by 1 is equal to 0, and 1 into 3 minus 1 into 0 by 1 equal to 3. So up to this we solve the RS table and find out this term is 0. What should we do? So if you find this kind of cases, you just replace this 0 by a very small positive value. Okay, or consider this 0 is not a 0, but this is a value of positive whose value is actually 0, but you should consider, let's say 0, instead of 0 you write it's a epsilon, and epsilon is actually 0, but for our calculation, let's say epsilon is very small value, like 0.000000001. Okay, do not bother about epsilon value, but just understand epsilon is a very small positive number. So once you do that, since the first element of a square row is 0, the element in the s to the power 1 row would be infinite, which I have also taught you. So to overcome this difficulty, we replace the 0 in the s square row by a small positive epsilon number, and then proceed with the tabulation. Starting with s square row, the results are given below. So this is the previous one. Once we remove once you try to make this s square coefficient epsilon, so that means remove this 0 as epsilon, and this is as it is. Then we proceed like epsilon into 2, that is 2 epsilon minus 3. It is given here 2 epsilon minus 3 divided by epsilon. Instead of 0 we write epsilon, which indicate 2 epsilon minus 3 by epsilon is actually minus epsilon by 3, if you consider. Or don't, okay, let's see after that, after finding the RS table. So this will be value, and we can see this is becomes 0. How? This into this term minus this into this term, so there is no term actually, so this becomes 0. And finally this into this minus this into this divided by this term, ultimately this remains only 3. Don't care about this equality. So this is actually the Rath table, and we can see that how to make the system stable. The system is stable if and only if the first row and first column, all elements, there have been no sign changes. And we can see here 1 is positive, this 1 is positive, this 0 we have taken positive small value. Then what about this? Is this positive? Is this positive? There is a question. This might be positive, I do not know. But you just think, if we take this epsilon is very small value, then multiplication of this will be very small than that of this. So ultimately epsilon into 2 is 0, na? Very small value is also nearly 0, which also we have taken that here. So this becomes, what happened, this to this term, this term becomes a minus 3 by epsilon. And we can see, observe that this is a negative sign. So there is a sign change from epsilon to this value and from this value to 3. So two sign changes exist here. And when there is two sign change exist, then system is obviously unstable. Clear? So there are two sign changes in the first column of Raoult tabulation. The characteristic equation has two roots in the right half of the S-plane. That is why the system is completely unstable. Do you get my point? Let's try to solve some other problem and find it out. Determine the stability of the system having following characteristic equations. The equation is s plus 1 into s plus 2 into s plus square plus 1 equal to 0. Guys, from this from this equation, it is very clear that first pole will be at minus 1, second pole will be at minus 2, and the third pole is a complex conjugate pole. Okay, that is s square is equal to minus 1, so s is equal to plus minus j. Okay, so this is two poles in the imaginary axis. So this system obviously imaginary stable. Okay, so without doing this thing also, sometimes we can guess, but whenever there is a question of some long question, then if you directly write the answer, you will not get the marks. So we have to go through the procedure. Okay, so my step is first remove this bracket, and the equation becomes s to the power 4 plus 3s square plus 3s, sorry, s to the power 4 plus 3s cube plus 3s square plus 2 equal to 0. And when you try to find out the Raoult table, likewise you need to write out s to the power 4. Here the order is 4, so it's a fourth order equation, and obviously according to the number of order, according to the order, there are same number of poles. So here order is 4, so you can see one pole here, and two imaginary pole here, so 4 poles are there. So you can write s to the power 4, s cube, s square, s to the power 1 and s to the power 0. Likewise, from this equation we have copied 1, 3 and 2 as the coefficient of s to the power 4, s to the power 2 and s to the power 0. Okay, and we have 3 and 3. Here we have 2 and 2. This two term comes from the multiplication and division formula. So 3 into 3, 9 minus 3 is 6. 6 divided by 3 equal to 2. Similarly, this is not, there is no term, this is 0, means this should be copied here. And when you multiply this 2 is 6, then this 2 is 6 by this 2, so ultimately this becomes 0. So what we need to do, replace this 0 by a small epsilon value and then proceed for the next value. So epsilon into 2 minus epsilon 2 into 0 divided by epsilon is equal to 2. So this is stable or not? This can be stable if all the first column element sign should be same. Here positive, positive, positive. This is 0, this is 2. So we consider this epsilon is actually a small positive number, so that for small positive value the system has to be stable. Okay, but we have find that the system is marginally stable. So it is very clear that if you have a 0 in any, at least any column, I mean any element of the first column, then the system is marginally stable. Clear? That means the number of 0 in the first column indicates the number of pair of complex conjugate pole. Clear, students? Fine. So there is no sign change in adjacent elements to epsilon in the first column. So a pair of imaginary roots are there. Hence the system is marginally stable. Remember this thing. When you have a 0 in the first column of the Routh array, then confirm that the system is marginally stable. Clear? So you take a notes, if the sign of the coefficient above the 0 element is same as that of the element below it, it indicates that there is a pair of imaginary roots. Okay, so with this we have completed the special case of the Routh criteria. Here are two equations I am giving for you homework. You determine the stability of the system having characteristic equation. So you take this equation and this equation, try to find out the Routh table and also the number of poles at the right hand side of the S plane and number of poles at the left hand side of the S plane, then comment about the stability. So remember, these two are given as characteristic equation. That means characteristic equation is the equation from CLTF or a closed loop transfer function. So do not bother about whether it is a closed loop or open loop. We have already given this is a characteristic equation. So obviously this is a closed loop one. So we have two equations. Okay. So comment about the stability. Okay. So with this we have completed the case 1 or special case 1, which is nothing but if there is a 0 in the first column or first any element of the first column, then what will be the stability. So we also came to conclude that if we found a 0 in the first element of the first column or any element of the first column, then the system is marginally stable. With that, I can add one more point that so the number of 0 in the first column indicates the numbers of pairs of complex conjugate pole. Okay, so thank you very much. We'll meet with some other concept, that is nothing but a special case 2, which indicates that if at least it completely row becomes 0, what should we do? Thank you very much. If you like the content, please don't forget to write a comment, share and subscribe to my channel. Thank you very much.